Going? All righty. So I'd like to welcome everyone to Immanuel Bloch's last lecture. And now is the time to ask any of the most pressing questions. I mean, not now, but at the end of the lecture, any questions you have for this venue. Remember, let them loose in the talk because this is your chance. Anyway, thanks, Immanuel, for being here.
Okay, all right. Hello back, everybody, and it's my pleasure to give the last lecture today. And as Ian said, feel free to just chime in anytime. So today I want to discuss a few non-equilibrium dynamics experiments that I think fit quite well to some things we have been discussing before, some things you've been hearing from Thierry, from Wasim, from others already, but maybe hearing them in other words is not so bad, also hearing them again. And finally, I hope we get to this really interesting new topic, which we had a lot of fun actually exploring. And I see Francisco here from Norm's group. So it was a lot of fun in that collaboration. I hope to tell you a little bit about this Parisi-Zhang universality in Heisenberg quantum magnets. A very interesting story. Okay, so let's get started. So mostly it's about spin physics today. So we're going to start very simple and just remind you again of the basics of the spin physics. And the basic of the spin physics in our strongly interacting atomic systems is for us the super exchange interactions. So these are these interactions mediated by collisional exchange. I think Wasim has probably derived this for you, that the energy scale of this exchange interaction is given by 4 times the tunneling matrix element squared divided by U. And okay, there's always this inconsistency in our community. Sometimes we call the tunneling matrix element T, sometimes it's J, whereas J actually should be J exchange coupling. So, but I guess you will figure out what I mean depending on the context. So here it would be the tunneling squared. So it's like the second order perturbative process where an atom hops from here onto the neighboring site with an amplitude T. And the intermediate state has an energy of U, and then it hops back with an energy of T, which gives you this basically 4T squared over U energy scaling. And if you have symmetric interactions between up, down particles in the system, and basically no asymmetries or no spin-dependent lattices, then what you get out of this second-order perturbative process is a Heisenberg model. And depending on whether you have bosons or fermions, you get a ferromagnetic or an antiferromagnetic model. So for bosons, you get ferromagnetic interactions. So this J exchange would be positive. And for fermions, you get a antiferromagnetic model where this J exchange would be negative. So there the spins would tend to prefer to anti-align. You can, of course, also rewrite this Heisenberg term in terms of its 3 components, the XX, YY, and ZZ interaction. And in our case, as I said, they're basically equal coupling strengths, J exchange here. If you do have spin-dependent potentials or Feshbach resonances, you can actually get an independent handle on this term and this term. And if you make them unequal, then you basically realize a more general class of spin models, the so-called XXE models. So that, of course, also interesting. But here today, we're just going to focus on the Heisenberg model in our system. And you can also rewrite the Heisenberg interaction, especially this XY part here, in terms of spin ladder operators. So you can write this XXYY term as S plus, S minus, S minus, S plus operators, where S plus is just a spin flip operator taking a spin down, flipping it into a spin up, and S minus takes a spin up and flips it into a spin down. Why do I write it like that? Well, I write it like that because it's very suggestive. It's very much like the A dagger A operator you have in kinetic energy. For just a single particle moving on the lattice. And indeed, this is basically kinetic energy for the spins. This is what makes them move around. So this is kinetic energy, like kinetic energy. And this here is like interaction energy that we're going to talk about. And we have to, think about the effects of those two terms separately, and we'll start with a simple case where only the kinetic term plays a role, and then we'll move up to a more interesting case also where this interaction energy term is highly relevant. Yeah, but it's really nice to think of it in this language. Then you know this S plus S minus is really just moving the spins around, and the SESE is the interaction term in the system. Okay, so let's start with something actually I did with Thierry back in the days. we looked at this problem of just looking at a single spin. We have a ferromagnetic chain, and we just take a single spin and flip it here on this side. And now we want to see what happens as this spin moves now around. And as I said, now the only term that's relevant is actually the S plus minus term. We'll see that in a second. And this will now start to flip-flop. We'll move this spin around and we'll start to delocalize the spin over our entire chain. So this is just our single spin impurity dynamics that we can then track. And to understand what's going on or how we can prepare this state, initially we start out, for example, with this 2D system. We chop it up into one-dimensional spin chains, which have no connection to each other. All the spins align, so you have this ferromagnetic system. Then we basically do the following. We shine in a laser which has this kind of spin-dependent potential, which shifts, let's say, the F = 2 state and the F = 1 state differently. So if you have two spin states and you focus this spin-dependent laser onto your atoms, it shifts them differently. And now if we shine microwave radiation onto the atoms, we can tune just one of those atoms which are in resonance here with such a transition. So let me actually, oops, sorry, go back here again. It's not showing the animation, sorry. So what should have shown, that's a pity, that we address with the laser then, for example, this column, and we flip all the spins in this column to spin down. So we've basically deterministically created this impurity in the system, and this impurity will now start to move in the system. So how can we understand its motion? So this is the initial state. As I said, we have this Heisenberg interaction term. We're in a ferromagnetic chain. Now, if we just have a single spin, and this single spin moves around in this chain. So if, let's say, this spin moves from here to here, then if you look at this term here, this term will be independent of wherever that spin's position is. So this is just going to be a constant offset in our problem, energy offset, that we can basically just neglect for this problem. So the interaction does not play a role here, because independently, wherever that single spin is on the chain, it's always going to give us the same energy offset. And therefore, we can just discard it. It's not going to play a role for the dynamical evolution. What will play a role for the dynamical evolution is this flip-flop term, the S plus S minus term. And as I said, this is just like the A dagger A term. And you've already actually heard in Wasim's talk, but I think you already heard in Adam's seminar, you heard what happens if you just have a single particle on the lattice and let it evolve. It's just a quantum walk. Basically just does a quantum walk. And the same is true for our spin moving now on the spin chain. It's just like a single atom tunneling on the lattice, on a one-dimensional lattice, moving around. And therefore, we expect the probability distribution of the spin after some evolution time to be exactly the same as the probability distribution of a single particle tunneling on an empty lattice in one dimension. And this is indeed what we see in the experiment. So here's the experimental data together with some theory plotted on top of that. So we start with the atom localized to position 0, or the spin flipped at position 0, and then we look at a certain evolution time in the system, and then we measure the probability of finding that spin up at some other position on the chain, and we're plotting that probability distribution then here after repeating the experiment many thousands of times. Of course, when we take a single photo of the system, remember, we're always going to just see one spin up. We just put one spin up into the system. So when we take the photo, we're just going to see one spin up. It's going to appear in random positions. And then we repeat the experiment many, many times and get the probability distribution. And this is precisely what you see here. And this probability distribution, the red curve here, this is precisely the analytic formula that you can see down here that you get for just a single particle tunneling on that lattice. It's just given by this Bessel function. And you can actually see that matches very, very nicely with what we see in the experiment. So single spin in a ferromagnetic chain, very simple, is basically just like a single atom tunneling on an empty lattice. It's just a simple single particle problem. Okay. All right. Now, yeah. Question.
Are you using the predicted J exchange value, or do you have to kind of fit that since it's not a extremely large U over J?
Yes, so we can. There are usually, well, it depends a little bit how good you calculate the U and the J. We typically have to, we do the simple band calculations. We have to modify those parameters that come from a single band calculation, because there are, higher band effects which modify, for example, the couplings. But this is a good way to calibrate this. Okay. And I don't know if you ask me now, the red curve, did we take the calculated single band model already, some adjusted ones? I honestly don't remember anymore. This was
okay. Yeah, that was the question. I was just curious.
Yeah, I don't remember right now. In the new experiment I'll show you in the end, we take this as a way of really calibrating J exchange independently. So this measurement is a way of extracting from the experiment J exchange, and we compare it to calculations. And typically, there's only about a 10% difference from your single band calculation for typical parameters, Caden. Okay.
Thanks.
All right. So that's simple. So let's do something more interesting, and let's try to look what happens if we flip two spins. Okay, so now we just do the same experiment where we go in with a laser and we rotate the spin, but now we don't do it with just a single spin, but now we do it with two spins. We rotate it, and now you see now actually this interaction term is going to play a role, because whether you have those two spins connected to each other is going to give you a different interaction energy, whether if they break up and are on separate places on the lattice. So there's not anymore the position of those two aligned spins, how close they are to each other matters in the interaction energy term. In the current term, in the case of ferromagnetic interaction, this is like an attractive interaction between those two spins. They really want to stay aligned to each other. Yeah, so it's a little bit like the smallest soliton solution you could think of. Yeah, there's a nonlinearity in the problem, and if you wish, you can think of this as the smallest elementary magnetic soliton you can form out of these two aligned spins. And now again, we have to now look what happens in the evolution of such a system. And this is now a bit more tricky because we have this term really matters now. It's important to say that this problem, actually a very famous problem in the context of spin chains and also, well, exactly solvable one-dimensional systems, because it was the problem that Hans Bethe studied when he invented the beta ansatz. So this was exactly the problem he was looking at when he invented the beta ansatz. Okay, so yeah, just to show you that looking for these things in spectroscopy in condensed matter, real materials is tricky. I don't know, Thierry, if you've showed some data on this, but I think what we can bring to the table here is this real space, real time evolution picture that we're really strong in. We're sometimes not so good in the spectroscopic data, where most of the time the condensed matter experiments are better. But in terms of real time evolution and real space observation, we really have a chance to do something new, to see something new. So, okay, so what do we get? What are the options for this system? So let's say we flip the two spins right next to each other. Now, there are two things that can happen. Either these things just move together through the lattice, as you can see here. Okay, so just think of it, they move together through the lattice, or they break up, the bound magnon breaks up and the two spins move independently. So these are basically the two things that can happen. So either, these two aligned spins move together as a bound object, as this soliton, or they break up and move independently as two independent magnons in the system. And so these are the two possibilities we can have. And this is indeed what you see. Here are some DMRG simulations where you have time on this axis here. You have the lattice sites on the horizontal. You flip initially two spins, and then you look at the evolution of the system. And you can actually see that when you turn on this JZ interaction, when you make this JZ term stronger and stronger, you see you see a breakup of the spins. This is this cone here. And you see a second cone evolving, which is exactly these bound magnons propagating now in the system. There's actually even a nicer way of plotting that I want to show you. I hope this animation shows now. That is the plotting the probability of finding the two spins at a certain evolution time at a certain position x1 and x2 on the lattice. So let's start with the two spins here initially right next to each other. So this is the initial state at time t equals 0. So this is the position of the first spin on the lattice. This is the position of the second spin on the lattice. So this is the first spin. and this is the second spin. Now it does work, but it went too fast. And you can actually see now what happens if we do not have this interaction term. Then basically those objects don't stick together, they basically just break up. So how can I see that? Well, think of these maxima, this probability maxima here. Whenever you find the second spin at a large positive x value, you find the first spin actually at a large negative value. Okay, so if this would be the 0 of our coordinate system, whenever the second spin is a large positive value, the first spin is a large negative value. So they really appear on opposite sides of your chain. So there's no binding of those two spins to each other. And this shows up nicely in this simulation. Now let's turn up the interactions. Let's go to the Heisenberg point where delta is 1. So we expect some bound state to form. And let's start again with the two spins right next to each other and do the same time evolution. Okay. Now you can see something different is happening. There's a little bit of breakup still of the magnon here of these two things next to each other. This is due to the fact that when we created these two spins next to each other, we didn't prepare a perfect eigenstate, a perfect bound state of the system, but it had a large overlap with the bound state. And the fact that it had a large overlap with the bound state, you can see on this diagonal. Here you can now see really those two spins are moving together through the lattice as this bound object as I promised. Okay, so this diagonal population now really shows us that these two spins stick together and they move together through the lattice. If we increase interaction energy more, what would be your guess what happens if I crank up delta more? Let's say I go to delta 10 compared to the kinetic energy term, the S pluses minus. What would you say what happens actually in that case? Any ideas? You're making this interaction term even stronger in the system. Just stay fixed, almost. That's true, you're almost getting there. So you're really increasing the interaction energy, the attraction between them, and you're decreasing the kinetic energy. So the kinetic energy is becoming smaller. So this thing is becoming much heavier. So indeed, they basically evolve very slowly. And you can see this here. Now I do this for 1.6. So just a slight increase in the Z-Z interaction. And now you see how they basically move much slower. This would be the same time that I have because I've just decreased the kinetic energy part. But you also see that there's much less breakup of the magnon. So it really means that the two spins polarized right next to each other are much better description of the bound eigenstate of the system. So they have an even larger overlap with the eigenstate of the system. And if I would go to delta even 10, then this thing, you wouldn't even see that anymore. These blobs on the side, there would be basically no breakup. They would really perfectly stick together because these two flipped spins directly correspond ideally to the bound magnon case. Okay, yeah, let's do the experiment. So we can do the same thing now. That was all theory. We can do the experiment. In that experiment, we can only do it at the Heisenberg point. We cannot tune the delta because we didn't have a Feshbach resonance in that experiment. But here you can see the data. So we can compare the experiment here, experimental data, to the theory at the Heisenberg point and to theory, for example, if you would have non-interacting spins, if delta would be 0, this anisotropy parameter would be 0. And you can indeed see, well, beautifully what I showed you in the theory, you can actually very nicely also see in the experiment. You can see the breakup of the magnon, so it's not perfectly bound, but you can also see on this diagonal, you see the propagation of this bound spins sticking together and moving together as a new entity, as a magnetic soliton through this lattice now. So we can really nicely detect this bound magnon very visually in this experiment. You know, by just looking how fast does this bound object propagate through the lattice, we can also compare to a beta solution. So in the beta ansatz, you can directly derive what is the velocity of these two objects sticking together compared to just free magnons. And what you find that the velocity of free magnons compared to the one of bound magnons is just 2 times the anisotropy parameter delta. So this is what you can see here. And we can do that. We can measure that. In our case, we find a 2.3 with an error bar of 3. So actually in very good agreement within our errors with what you get directly from the exact solution of the problem in beta ansatz. Okay. A question, please shoot.
Yeah, so I missed in the beginning. Is the exchange? You're talking about the ferromagnetic exchange.
Leo, you're using the other microphone again, so you sound like Darth
I
Vader.
can roughly understand you. Yeah, maybe for you. Okay, that's a microphone problem. Okay.
Can you hear me now?
Yeah, perfect. Perfect.
Yeah. You're using your exchange of the ferromagnetic.
Yes.
Is that something you have control over? What determined whether in your experiment J is a positive or negative ferromagnetic?
Yes. So for bosons, what you get from the Hubbard model is always ferromagnetic.
Okay.
For fermions, it's antiferromagnetic. We'll come to that in a second. So what I showed you is experiment with bosons,
Right.
strong interacting bosons, Hubbard model.
Mhm.
If you use fermions, you get antiferromagnetic. Yeah.
Okay. And the bound state energy is roughly JZ, 2JZ. Is that?
Yeah, in the large regime, it's something like that. Yes.
Okay. Thank you. Thank you.
Okay, so let me actually switch.
I also had a question.
Please shoot.
In your previous slide where you were comparing theory and experiment in terms of motion of the bound magnon in the interacting and non-interacting case.
Yes.
I guess here it seems in the experiment there is more of a bias of them, like in the delta equals 0 case, it seems the theory is equally treats equally the magnon moving together and separating, but in the experiment it seems it separates more. Is there a difference there?
In the experiment, we can only in this experiment, we could not do the delta equals 0 case because we didn't have tunability. We can only do the delta equals 1 case, which is what we get naturally from the from the Hubbard model. So this is just for you that I'm just comparing to delta equals 0, just to show you that if it would be delta equals 0, it would look completely different, the probability distribution, what I should be seeing. Okay.
I see.
So we should compare this theory for delta equal 1 to this experiment, which was done under pretty much the same conditions.
Okay.
Okay. So it's not perfect agreement. There's some slight differences, but it's an experiment. Okay. So there are some imperfections, but I think that the main feature that you can still see, a little bit of the breakup and this diagonal, strong diagonal, that's very clearly present. Actually, here you can nicely see for shorter evolution times, you can see the non-bound part, because simply your initial state of the two flipped spins is not 100% overlapping with the true bound state at the Heisenberg point. If you would, of course, have a method which would be more intricate to prepare the true bound state wave function, then of course you would just purely evolve together. But that's a bit more tricky to prepare that.
Thank you.
Okay. Any more questions on the ferromagnetic chain before we move to the antiferromagnetic chain? And look at stuff.
Sorry, I have a question regarding the breaks of the magnon looks to be more easily breaks down when the magnon stays at the center, right? But otherwise, if the magnon stay, let's say 1/4 of the position, actually they stay the magnon stay there very clearly. But when the magnon stay at the center, it looks like it's more easier to break down. Is there any reason for that?
I'm not sure I follow your interpretation. I mean, here we're just plotting just the experimentally measured probability of finding those two spins at the two positions at some evolution time. Okay. So
yes.
we're always starting. This is always the initial state. This is the state at t equals 0. You see, we just flip two spins with very, very high probability. We don't do anything else. Okay. And then we let the system evolve. And what you see in this time evolution, what happens, you have part of it, which is really this bound magnon, which moves on the diagonal where the two spins move together. But you have this other part, what can happen that the magnon, that these two spins, they just break up and they just then move in opposite directions. And they're basically anti-correlated in space, which is what these these blobs give you.
Yes. So what does the max value, the max magnon, the blue dots means? It means it's more easily to stay there, right? Or you have one higher...
So this means, so you're asking, what does it mean if you have two blue dots here? Or So so the color scale just tells you the probability of finding one spin at the first spin at position 1 and the second spin at position 2. And this just shows you have a very high probability of finding them right next to each other, if it's that. Okay. And if so this would be the lattice axis, this diagonal would be the lattice axis, and the orthogonal direction would be the relative position. So they're right next to each other, and they're moving along this diagonal, the spreading along the diagonal that you see in the theory and in the experiment. This is precisely now the wave function spreading of the bound magnon. Okay, the bound magnon will have a probability distribution where it will appear. And this probability distribution, if you would basically, this thing along this axis is the probability distribution of the bound magnon.
Yes, maybe I can ask in this way. So why is the possibility of finding the magnon along the axis not equal? So you have a maximum possibility to find the magnon right on the chain. So
well, in the theory, it's symmetric, right, to the middle point. In the experiment, maybe not, because it's an experiment. But in the theory, it's always symmetric, right? It has some modulations, right? Like this, if I do with the wave function. But that's what you expect, right? I mean, if you have a single particle walking on a lattice, you also get a probability distribution, which we saw before, which is not, just not uniform or not Gaussian. Think of the bound magnon just as a new object with an independent kinetic energy, and this object is now performing a quantum walk on the lattice.
Okay.
That will give you a probability distribution like what we saw in the previous case for the single spin. Remember the single spin case? Let me go back here. Actually, let me do it like this. Remember the single spin probability distribution? That was a single spin moving on the lattice. It also has some interference pattern, right? And now the bound magnon will also have some interference pattern. It's just a new object with a much heavier mass. And in fact, that what is beautiful, there's not only, I didn't show you this, there's not only, you not only have the solution in the ferromagnetic chain for two spins sitting right next to each other, but they are solutions for so-called L strings, where you have a block of L spins aligned to each other. They really form a new entity and just move as an entire block through the lattice, but as a new quantum particle. But of course, this now motion of this block is a highly correlated motion, and it can only happen as a higher order process. And therefore, this object would be a very heavy object with a very small velocity.
I see. Thanks a lot.
These are exact solutions coming out of beta ansatz that you can have. And we just looked at the simple one, the two bound magnon state.
Okay, thanks.
There's a question from Grace. Can you re-explain the relationship between velocity of free? Yeah, I didn't really explain it, Grace. I just took what we get from this beta ansatz solution. So this is what beta ansatz, the dispersion relation for these L strings, what we get, what you get. And from that, you can, of course, just from the dispersion relation, you can derive the group velocity. And then you can compare it to the single magnon group velocity. And what you would get is precisely what I showed you here, that the single magnon to the bound magnon velocity is just 2 times delta. That comes from the beta ansatz solution. Okay, very good. Any more questions?
You said, do you observe like 2, 3, 4 higher magnon bound state?
We did not. We didn't try that. We could try that again. That would be interesting. They will be more difficult to see because they will move even slower, right? I mean, they will be heavier and heavier. There's been, I think, a recent experiment, maybe Thierry knows it, I think a condensed matter experiment where spectroscopically they were able to detect these higher L strings also spectroscopically in real materials.
So first, in condensed matter, it's usually the antiferromagnetic system which is realized because the spins are made of fermions. But indeed, there are several experiments where people observe the bound and anti-bound states of the let's say which appears in the beta ansatz solution. They usually manifest themselves as the line in a spectroscopy experiment. There is not this very nice real space tracking that one can do with the cold atoms.
Yeah. I mean, you always have then also the possibility that this 3 state, for example, L3 L string state can break up into a 2 L string state and 1 L string state. And so there are more possibilities. But yeah, we should maybe go back and do this experiment again. We just, now we have much better control. We should maybe go and have a look again how far we can push this.
But what about the possibility of, let's say you start out with a 1 magnon or 2 magnon, isn't there a process where it grows so that domain walls separate the way Terry described? Like, so you have 2 domain walls, spin 1/2 domain walls that.
I think what you refer to, Leo, is the antiferromagnetic side.
Come there. Let's do that now. Let's go there now and have a picture at what the antiferromagnet is doing. That's what I will show you now.
But even for a ferromagnetic one, it seems like you can grow the L string, the string.
Yeah, you can grow the string. You can make larger strings. Absolutely. No, those are true bound states of larger. They can become bigger and bigger, but they become heavier and heavier and just also more fragile. Yeah, to break up. Okay, great. You're very interactive today. That's fun. Cool, good. Okay, so let's move to the. Let's do the Fermion case. And I know you heard about this already in Wasim's talk and Thierry told you, but let me just do it again because it's such a nice really thing, and to contrast it also to the ferromagnetic case. And it's basically about doing a similar experiment in 1D. We're not gonna, actually what we're going to do is we are going to look for so-called fractionalization of an electron. In our case, we will have the atoms that mimic the electron. But let me first say, okay, you know that the electron is an object as an elementary particle. It has 2 quantum numbers, the charge quantum number and the spin quantum number. And you also know that in free space, you just cannot rip the electron part into 2 objects where one carries the charge or one the spin. It's really one entity. And what's really remarkable that in solid state experiments, and the one I'm going to show you, you can do that. You can break it up into 2 quasi-particles. When you inject such a electron into the right host material, it can break up into 2 quasi-particles, one which carries the charge and one which carries the spin quantum number, and they become deconfined, meaning that they can basically separate over arbitrary large distances. Okay, so that's what we call deconfinement of these quasi-particles. So you so to say liberate now the quantum numbers that were so intimately attached to the electron can now be liberated and can propagate independently. Okay, the system where we do this is a 1D antiferromagnetic chain. This is spin correlation, for example, that we measure in this antiferromagnetic chain. So we know it has nice antiferromagnetic correlations. Here's just a single snapshot of, well, a non-typical snapshot. It looks where we have spin ups and downs resolved in this picture. So in the lower chain, we have the spin downs, upper one, and we have the spin ups. They were separate. They were in one chain before. And that's actually something we always draw in cartoon pictures, and Thierry probably also do the cartoon pictures like this. But this is, of course, the picture of a Néel state of just classical up and down spins. But we have to keep in mind that we're talking here about Heisenberg systems, Heisenberg antiferromagnets with entanglement in them, but we just don't have a good way of drawing that. And the intuition actually in this Néel state is also still quite good. Okay, so now we're going to do the trick. We're going to do the impossible. We're going to split the electron and do that. And here's my cartoon picture again that probably saw. We take this antiferromagnetic chain of our atoms in the lab, and we basically shoot out with a laser beam 1 atom. Okay, so we shoot out 1 atom, and we look at the dynamical evolution of the system. Now, if you look at the dynamical evolution of the system, you've made a hole, and this hole will now start to propagate in the system with the tunneling energy. But you actually see there's another object that you've created next to this charged object, the holon, the hole moving. You've created this spinon in the system, and this spinon is a spin 1/2 particle. And this spinon can now move completely independently from the charge on, from the holon. So that's why we speak of deconfinement. And that's a very special feature of 1D. In 2D, you get completely different physics, as you also heard or will hear from Thierry. You've heard maybe also from Wasim. So we're just going to stick with the 1D case here. So do you all remember? Let me just remind you again also why this is a spin 1/2 object, because kind of if I look at it as an atomic physicist, you think, oh, 2 spin 1/2s next to each other. shouldn't that be a spin 1 or spin 0 object? Why is that a spin 1/2 object even? And I think at least the layman version, and I think here you showed this cartoon also, the way to understand it is to not do charge fractionalization, but to do spin fractionalization. So imagine again the same spin chain that I showed you, up, down, up, down, up, down, up, down. And let's imagine we go with a laser beam now onto this spin and rotate it to up. If it would be down, we rotate it if it would be up, it rotated to down, but if it's down, we rotate it to up. So we just do a spin flip, a pi pulse on that spin, okay? So what does that mean? That means we made a delta S equal 1 spin flip, right? Because we changed the spin from +1/2 to -1/2, so we changed the total spin by 1. And now let's have this system evolve for this super exchange interaction, which basically is just this flip-flop interaction now. So basically, if we have now this configuration after flipping the central spin, and you now move this spin over here and this one over here, and the green one comes in here and the green one here, you have this configuration a little bit later, and a little bit later you have this configuration here. So you see, actually, you get 2 of these spin-ons out of originally this delta S equal 1 spin flip. And from that, you can immediately deduce you created 2 equal objects. You change the total spin by 1 in the system. And if you create 2 objects that move independently, then intuitively, these objects have to carry spin 1/2 quantum number. I mean, that's at least my layman experimentalist view of how to understand this, how we can think of this, of why this spin-on is actually a spin 1/2 process. Actually, this process, if we would do this experiment, we didn't do that, but it would also be interesting to do, we would actually be measuring spin fractionalization, because you change the spin by delta S1 and you see how it breaks up into 2 spin 1/2 objects. Maybe you can try yourself, if you do this in a ferromagnetic chain, you do a ferromagnetic chain and you flip 1 spin, this is not going to happen. You're going to stick with 1 object, which is just delta S1, which is an S equal 1 object, and that's just a magnon, of course, and there's no fractionalization. So as we said, this is really something intimately connected to the antiferromagnetic chain that we have in the system. Okay, so seeing that you could see this, actually, well, I should say there are beautiful condensed matter experiments on this spin charge fractionalization by, for example, Amir Jacobi's group. And but I think the first ones to note it in the context of cold atoms was the group of Corona Kollert, Uli Scholwerk, and Willi Zwerger, who did like first DMRG calculations showing that this is a really nice setting to see this in real space. Okay, here we see that. So again, let me show you the data. We basically kick out an atom out of our spin chain antiferromagnetic chain. So at time t equals 0, so this is evolution time versus position on the lattice. At time t equals 0, I make a hole here. So my hole density is large here. And as this hole now propagates in the lattice, it just does a quantum walk on the lattice. And the probability distribution after some evolution time should just be the probability distribution of a single particle walking on the lattice, approximately. And this is indeed what you see. So you see there's a cone, from which we can derive a velocity. And there's some interference structure in between. If we make cuts through this probability distribution, we see that it's really nicely following this quantum walk dynamics that we've seen now many times. For the spin, I can look at a different quantity. I can look at the next neighbor spin-spin correlator. And at time t equals 0, when I made the hole, next to the holes, the spins are aligned. And I can just look how this object propagates. This is basically trying to look how the spinon propagates. And indeed, you see there's also a cone here that you can see. There's no interference pattern. And the reason why this interference pattern gets washed out for us is because the temperatures are slightly too high in our experiment to see that. Otherwise, you would also see a nice interference pattern in the probability distribution of the C1 correlator, the next neighbor spin correlator in that system. But you can just now take the width of the cone as a function of time and plot the width of this distribution as a function of time and really directly calculate what the propagation velocity would be. So I'm just plotting for my whole distribution, my width as a function of time. For my C1 correlator, the distribution as a function of time. You see it evolves linearly, so we can just put a slope through it, and the slope will tell us basically the velocity of the system. And indeed, you can see that the holes have a much faster velocity than the spinon in the system, which is of course also what we expect in this spin charge separation, because they're very different dispersion relations. Now, I want to show you why having these quantum gas microscopes at hand really allows you to measure more. Because you could say, well, just seeing two objects propagating at different velocities, that's not really precisely showing the essence of fractionalization. You're just seeing two objects, with different propagation velocities. Let me show you that now, if we look at a higher order correlator, we really can probe the fundamental aspects of this spin charge fractionalization in a much nicer way. And so what I'm doing is the following. I'm again doing the same experiment. I'm kicking out this spin here on the central site, but now I'm measuring this 3-point correlator. So what does this measure? It measures how are the spins aligned around a hole. So that's 3 points, right? We're measuring the spin here correlated with the spin over here at site i+1, conditioned on having a hole in between. So it's a 3-point correlator, and that's already something you cannot measure in a condensed matter experiment, but we'll see this is actually crucial. So now, as time evolves, let's look at our cartoon picture. How does this higher order correlator evolve? You actually now see, well, you get the spinon over here. Here's the spinon, and you get around the holon moving over here, but you see now this hole, this spin environment around holes has now completely changed from being positive initially, because the spinon was still located at the same position as the holon, when we created it. But when the spinon has moved away, the spin environment around this hole here is now antiferromagnetic. Instead of being ferromagnetic at time t=0, when the spinon and holon were basically still at the same position in space when we created them. So now we see that after a long evolution time, what we should be seeing is that the spin correlator around the hole will turn from positive to negative, indicating basically that our spinon has moved away from the holon. So this is a direct proof that the spinon is not anymore attached to the holon, okay, through this 3-point correlator. So the hole got rid of the spin basically, and this is indeed what we see in the experiment. So you start out with a positive spin-hole-spin correlator, indicating that at time t=0, those spins were aligned next to the hole because of the antiferromagnetic chain that you had. And then, as you let the system evolve, you basically go to a negative value, and then you settle to some negative background value of the spin correlations around that hole. So that really is direct proof that you've removed that spinon from the holon, and you have this deconfinement phenomena that I introduced to you before and that I told to you before about. Okay, maybe one final thing. We are doing this all at finite temperature. We're not at 0 temperature. So how do we have to think about that at finite temperatures? Well, let me first say at 0 temperature, the fractionalization is perfect in the following sense that whenever you create this, shoot out a particle, you remove a particle or you inject a particle, you always get exactly one spinon and exactly one holon. So fractionalization into the two constituents is perfect. At finite temperature, simply because our spin environment is not always perfectly antiferromagnetic, we already have spinon fluctuations in the system. We don't create the spinon with 100% efficiency when we shoot out a hole, but each time we make a hole, so we have very high probability of creating a hole in the system. But the probability of creating a spinon at the same time is reduced at the finite temperature. Okay, so that's basically this efficiency, this one-to-one efficiency at 0 temperature is reduced in the case of finite temperature. And this is how you should think of fractionalization at finite temperatures. Okay, any questions on that?
I guess I have two questions. You showed us that each of the particles does a random walk. Is there a way to engineer interactions? Like, is there a regime where the holon and the spinon can still are not necessarily bound, but can still have some interactions?
Well, that's when you go to 2D. That's exactly what happens when you go to 2D, where you introduce something like a string tension between the holon and the spinon. And that's what gives rise to completely different solution in 2D. So in 2D, if we shoot out a hole, what actually happens is you form a polaron around that hole, where you can think of as this, if you so Eugene and Fabian had a very nice recent description of this. You can even think of this really as a bound object of a spinon and a holon bound together by some string tension in the system, indeed. And this string tension goes to 0 in the 1D case. So here you have perfect liberation, so perfect deconfinement. And as soon as let's say we go to a ladder, for example, or to larger dimensions with stronger coupling strengths, then we would introduce this string tension, and we can see this, crossover, this completely different behavior from the spinon holon deconfinement to forming a polaron, a spin polaron around our kind of impurity, doped impurity that we have in the system.
And I guess another question is, because we have Heisenberg antiferromagnetic interactions, but it seems like we're only looking at correlations in Z. Is there some additional information like SX, HSX that we're missing out? Or
yeah, you could look at those. Would be easy if you just would want to measure the same correlator for the 3-point correlator with, instead of SZ, SZ, SX, SX, we could do that. That should give the same thing, of course, because we have SU2 symmetry. So that should give the same thing. We can measure that by just having a global spin rotation before we do the detection. So you just do a global pi/2 pulse. What you can do, but you can do something that's even more interesting, or maybe even more flexible. If you measure SZ on that side, but SX on that side, okay, that would give you an even more intricate object. That's more difficult to do, because that means we have to do a local change of the measurement basis before detection. That's also possible. I could just focus a laser beam here, do a spin rotation by pi/2 there, and choose the measurement basis there, and then I could be even measuring SZ whole SY operators. So there's a lot of possibilities here, as you can see. And though they are interesting, they are not academic things. These operators really are very crucial in identifying the properties of this system. Okay, any more questions on that? Okay, so since we have good in time, so actually let me show you now how this dynamical feature is actually related to a hidden order of the antiferromagnet in the ground state. So we saw this spin charge fractionization as a dynamical feature, but I want to show you that it's actually already present in the ground state, and in a very beautiful way actually present in the ground state. So we take the one-dimensional chain, and now we dope it, we put holes into the system, but we don't do it in this abrupt way of just kicking out particles, but we really dope it initially, and we're asking, what is the ground state of this 1D chain when we dope it with holes? Okay, that's the question we're asking. Well, of course, we want to minimize the total energy, and we have two conditions that we have to fulfill. There are the holes, and the holes have minimum energy when they delocalize, right? They're like particles, and their kinetic energy is smallest when they are delocalized. On the other hand, we have this condition that the spins, they really want to align antiferromagnetically to minimize magnetic energy cost. So we have to find a ground state which minimizes both those conditions at the same time. And the cartoon state that does that is the following state, where you basically have this antiferromagnetic order, up, down, up, down, up, down. And you have the hole here, somewhere there's the hole, and the hole is delocalized in the system. So the many-body state would be a superposition of these different ground state configurations, with the hole being everywhere. So the hole is delocalized. And around the hole, you have antiferromagnetic correlations. Why is that favorable? Well, you can immediately see that if this spin moves into this hole, so moves to this side here, then it's antiferromagnetically aligned with the neighbor. And that's obviously favorable for that spin then to have an antiferromagnetic alignment around the holes in the ground state of my system. Okay, so this is the ground state configuration. This is, I think, Thierry, you would call this a topological excitation, because a single hole, and that's quite strange in 1D, a single hole has a global effect on the entire system. In the ground state of the system. So not only a local effect, this small hole, but this small hole will change the entire ordering of the system in the topological way. And the way to see this is the following, to say, well, let's denote the types of orderings that we can have by a so-called parity quantum number. And let's say we call a down, like let's say, oh, sorry, let's go back here. Let's say we call this, oh, why is it not, sorry. Here we go. So let's say we call this down, up, ordering +1, and up, down, -1, the two types of orderings that we can have. Then we can see actually that what a hole does is like a domain wall for the parity in the antiferromagnetic order. So a single hole will flip the parity of the antiferromagnet completely, even thousands of sites away from that hole, okay? At t = 0. At finite temperature, of course, correlation lengths will always be cut off. Now that we understand, we can measure that. Okay, so let's have a look at this measurement where we see this. So this is now a complicated object. We're measuring again the spin-hole spin correlator. So measuring again how are spins aligned when there's a hole present. So we're measuring the spin at site the spin at site I correlated with the spin at site I + D, conditioned on having a spin at site I + S. Now this I + S, this S can have two values. It can either be between the two spins we're correlating, so S can be smaller than D, and then we know we have the parity flip in the domain wall, or the hole can be outside of the two spins we're correlating, and then of course it will have no effect on the parity of the antiferromagnet. And this is what you can see here. So this is the distance between the two spins. This is where the hole is. And now when S is larger than D, so we're basically in this upper quadrant here, we see this nice antiferromagnetic ordering, down, up, encoded in the color of this correlations. Now, when you move down, when you move to the case where S is smaller than D, you see that red has turned to blue, blue has turned to red. So really you had this flip of the parity of the antiferromagnet. And I can make this even more visible to you if I take out this nasty ±1 staggering that we have there and just multiply by -1 to the power of D my data. You can directly reveal the parity of those blocks, and you can see when there's the hole outside of the spins, you have one type of parity, and when the hole is inside of the spins, you have another type of parity in the system. Okay, so you can really directly measure this effect, this topological effect of the hole on the system. Now that you understand what a single hole does, you actually understand what many holes do. That's now easy because there's no difference. Each time there's a hole, there's a parity flip from -1 to +1, +1 to -1 in the antiferromagnet. And now if you look at this picture, take a look at it and try to see, okay, how is this state ordered? Well, you can actually see if you would just remove, fictitiously in your head, remove those holes, squeeze the system together as if there were no holes. Then you see, well, then it's like down, up, down, up, down, up, down, up. So it looks like a perfect Heisenberg antiferromagnet to you in this fictitious squeeze space where you have removed the holes. But remember, the holes are a fluctuating quantity. The holes are moving around in the system. But you know, when you see them, if you could see them and you could remove them in this fictitious squeeze space, you would actually see perfect Heisenberg antiferromagnet again. But if you cannot remove them, you have a problem. For example, if you measure two-point correlation function, if you measure how is this spin correlated with this spin over here, it would give you a 0 result in the presence of fluctuating number of holes. Because, you know, each time there's a hole here, it will flip, you know, where the spin points up and down. If you average over the different configurations, it will give you a 0 result. Now we see we have this Heisenberg antiferromagnet in squeeze space. That's nice. And this basically ordering can be cast into a mathematical form of the wave function in 1D through the beta ansatz in the limit of infinitely strong repulsions in a very beautiful way. So you can write down this very complicated many-body wave function of the fermions on my 1D system, on my 1D lattice with many holes in them. You can write down as a product of spinless fermions defining the position of the electrons on the lattice. So this is the density part of your wave function, multiplied by a magnetic part, a Heisenberg part, where you basically here have this antiferromagnetic order in squeeze space at the positions of the electrons in my system. And this is where the magnetism lives, okay? And this factorization into density and spin part. So this is a density part. And this is the spin part, the magnetism part. this is the manifestation of spin charge separation in the ground state of the system. Okay, that you can write this as a factorization. All right, yeah, let me not talk about the string order, but let me just say, I keep those in the notes for you. Let me just show you that you can measure this also, okay? So let's take this 1D chain and put a lot of holes into this chain. And let's measure, first of all, the 2-point correlation function. So I'm measuring as z of I as z of I plus d. And this is what I'm measuring. And what you will see is that, you know, and I'm plotting it versus distance here, d. If the distance is 1, I'm just correlating the spins on neighboring sides. There's no hole in between them because they're right next to each other, the spins. And then they are antiferromagnetically aligned, and we see basically a nice negative antiferromagnetic correlation here, because there's simply no holes here. But of course, as soon as we go to distance larger than 1, there can always this hole come in and squeeze into the system, and that will fluctuate, make those spins on the different sides fluctuate on this side I plus d. And if we average over all those possibilities, it will basically average out to 0. And this is what we see in the experiment. We see basically 0 correlation function in this 2-point correlator whenever we go to distances larger than 1. And if you look at that picture, and if you would measure that in an experiment, you would say, well, there's basically just no interesting antiferromagnetic structure in the system. Yeah? But now we go to the squeeze space and look in squeeze space correlations. And then if we do this squeeze space picture, we see that we now can see the antiferromagnetic correlations emerge again. So if we remove the holes from the system, and in these quantum gas microscope pictures, we see the holes, we see where all the spins are, where the holes are. So we can take them out because we see them in the experiment, in each shot of the experiment. If I take the holes out and measure what the antiferromagnetic correlations look like, you see we get nice antiferromagnetic correlations again. We can detect these hidden correlations in the system. All right, good. So that's all I wanted to say about antiferromagnets. Any questions on the antiferromagnets before we switch to the last topic? Spin charge fractionization, 1D, 2D.
Could you explain the last plot again, where the C was going a little up and down? I guess I didn't understand what was plotted.
Yeah, so basically what we plot there, actually what is plotted there is a string correlator, but you can think of it as the antiferromagnetic correlations in this fictitious space where you remove the holes. Okay, so you basically remove the holes from the system, because you see when I take a photo, I get a photo like this, for example. So I see a spin up, a spin down, a hole, a spin up, a spin down, a spin up, a hole, and a spin down. That would be one shot. If I remove those holes now from the system and measure the spin correlations between I and D, you see you get perfect antiferromagnetic correlations again. But if you don't remove the hole, if you don't know where the hole is, you know, then you cannot do that trick. Because and if you're now measuring the 2-point correlator at a fixed distance, and there are fluctuating number of holes between your side I and your side I plus D, this will mean actually the spin, you know, on this side I plus D will fluctuate in its orientation depending on the number of holes that you have in there. Whenever you put another hole in between the two spins, it will change the orientation again. When you average over all those configurations, you get 0 result, which is the blue curve. But if you can take that out, if you can account for the holes, that's the trick. Then you can see this antiferromagnetic correlations that are present in the system. But you need a global view on the wave function of the system. You need to be able to see each individual electron and hole in the system. You need to know what's going on each lattice side to do this trick. So this is like, you know, it's a nice example of a hidden order, as condensed matter physicists would say, because it's hidden. People, they talk about hidden order as standard condensed matter physicists, because in any normal experiment, you cannot measure this. You can only measure 2-point correlation functions. And therefore, this order that we saw is present in the system, you would not be able to reveal that in the experiment. I would say, well, in the era of, you know, quantum simulators and whatnot, it's a bad name because we can measure these things. They are not hidden to us because we have the microscopic view on the entire system. And that's the powerful thing. So you can now think of detecting new types of orders in these quantum many-body systems by looking at these kind of special kind of correlation functions, higher multi-point correlation functions. And that's something I maybe want to pass on to you also if you start working in this field. So think of, if you have some topological phase, some many-body topological phase, what is the non-local order parameter that corresponds to this phase? And maybe we can measure it. Okay. Any more questions, comments?
So maybe, may I understand it like in a system with many holes, the topological properties are actually correspond to the hidden order, right?
Yes, you can only reveal this antiferromagnetic order if you know where the holes are. Yes.
So my question is that to experimentally observe this kind of hidden order, I mean, is this related to or affected by the finite size? So since you are doing the microscope, maybe you don't want many large system size, right? Or it doesn't matter?
That doesn't matter really, no. That doesn't matter. I don't think that matters. I don't think that matters. I'll show you a large system now in a second. A larger one at least.
Okay. Cool, thanks.
Okay, good. Okay, let's move on to the last topic. It's really something very new, but you know, we're at the end of the lecture, so we can talk about the latest stuff, maybe also new stuff, which is, at least we're excited about it. And this is about this Polarization Universality. And as I said already, this was a collaboration with Norm's group. Francisco was involved, Sarang, Gopalakrishnan. And yeah, so let me tell you what it's about. So let me tell you first what is this Kada-Parisi-Zhang equation. Actually, a very famous equation in statistical physics by these three famous people, Kada, Mehran Kada, Giorgio Parisi, and Jijing Zhang, and which describes the growth of interfaces. So you have a height field, which describes, for example, the height profile of an interface, and it describes how this height field grows as a function of time. And the crucial part in this, the really new part, the critical part is this term here, this nonlinearity. It's a nonlinear stochastic partial differential equation. It describes a stochastic variable, this height field. So this is not just a function, it's a stochastic variable. So it has some mean, but fluctuations, right? We'll come to that in a second. I'll make that visual in a second. So you have this stochastic partial differential equation with this strong nonlinearity term. If you don't have this nonlinearity term, if this is not present, then it's the so-called Edward Wilkinson stochastic differential equation, and that's easily solvable. But the problem starts with this nonlinearity. And that's why also, you know, this equation is so interesting also for mathematicians. They've been not able to solve this equation for a long time. And Martin Heira actually was one of the first people who was able to solve that. And he got the Fields Medal for that in 2014 for solving this equation. Okay, so it is not only interesting from physics, it's really also a great maths problem. Okay, so let's see, why is it interesting? It's actually a problem. As I said, it's about interface growth, and it actually occurs quite universally if you look at different phenomena. So you can have that in, you know, bacteria growing, tumor cell growth, liquid crystal, even coffee stains, burning paper, snowflakes. As I found out, there's this phenomenon that's called a fluff fire. So I don't know, there's this fluff from this, you know, that you have from this plants that grow in the spring, and they have sometimes covered the whole lawn by this fluff. And actually, it's interesting. I didn't know this. If you Google a YouTube it, you see there's this beautiful, you know, videos where you can see how a fire of this fluff burns. So the lawn is actually completely protected. It's just the fluff burns, and the fire front actually also follows this Kpc equation. So it's also something, even in forest fires or fluff fires, you see this fire front. So it's really a universal phenomena in this growth of interfaces. And to get a better understanding of what this nonlinearity does, we just can look at a game of Tetris. So let's think of Tetris in terms of understanding the interface growth. Think first of all of a very simple Tetris where you just have this boring single blocks, and they drop down in your columns, and they drop completely independently in those columns. So you just rain down blocks, and the blocks, the columns are completely independent from each other. And then, of course, what you would get is that you would get an average growth here of this height field here, and the fluctuations that you would get. What would be your guess for the fluctuations of this height field as a function of time? If we have a constant rate of deposition, then we drop into this block. What would you say would be the fluctuations as a function of time? How would they grow?
So it's like a random walk, so square root t.
Yeah, exactly. So random walk, square root t. Perfect. Square root of t fluctuations in the height profile. Perfect. Now I changed the game just a little bit. I'm working now with sticky blocks. So whenever this block drops down here and comes next to this side, where there's already an adjacent block, it will stick to that block. Okay, that's something for interface growth, which can happen, is quite natural to happen, that you have such a sticky kind of process present. And if you do this sticky kind of Tetris, that's exactly this nonlinearity term. The thing looks completely different. You can also see that I've plotted for you on the right how the height profile would look like in this sticky process, and you can see it's something completely different from this random deposition model. We speak of it also as a ballistic deposition model. And actually, I have this animation which shows this. This is how Kpz looks like in this ballistic deposition model, and you see it looks very, very different from just random blocks raining down. Okay, you have a very different height profile. Okay. Now now let's talk about Kpc universality. So we have this height profile, we have this model, and now it turns out there's a universality class in how this height profile looks, how the fluctuations in this height profile actually look. So first of all, again, we have an average height field that will be growing. We have fluctuations of the height field at a certain column. The fluctuations of this height field in the random deposition model, we said were growing like t to the 1/2, like a ballistic, like a random walk. Actually, here they grow like t to the 1/3. Okay, so the scale of the fluctuations is t to the 1/3. And the distribution function from which you draw, let's say, your random variables, remember the height field is a stochastic variable, so it has some average growth term plus some fluctuations. This sets the scale of the fluctuation. And then we have some random number that we have to draw from a universal distribution. In the case of the Brownian motion or just diffusion that you had before, this would just be a simple Gaussian. Here, it's a different function. It's the so-called Tracy-Widom distribution function. So it's a completely different distribution function. It's called Tracy-Widom. And it has some special features. It has actually, I've plotted it here for you. It's an asymmetric distribution function. So it's not symmetric. So it has some skewness to it that is very characteristic to this distribution. So these are the two things or three things that are very characteristic that define this Kpz universality class, that the fluctuations in your height field grow with a scaling of 1/3 in time and have this Tracy-Widom type fluctuations. And the dynamical exponent connected to that connects length and time correlations. There's also actually transverse correlations here in the transverse direction, and these transverse correlations, they grow in time like t to the 3/2, t to the 2/3, so t to the 1/3/2, where z is the dynamical exponent, z being 3/2. Okay, so this defines this universality class of a fluctuation. Yeah. All right. So
there's a question. It asks if the sticky Tetris gives rise to a fractal.
Yeah, I'm not so sure actually. I would have to check that. I don't know if it's a fractal structure. I don't think so, but I'm not sure. I have to check that. Okay, so everything I've been telling you, I mean, why am I telling about this classical physics process, right? I mean, this is all classical physics. There was this quantum surprise actually in 2017 and 2019 by papers from Thomas Porschen's group, who found out that actually in infinite temperature spin transport in Heisenberg quantum magnets also seems to follow this Kpz universality. So first kind of example for a quantum system that shows actually also this Kpz universality. That was quite striking. So what was the evidence? The evidence was the following, that let's say you put a single spin in an infinite temperature one-dimensional Heisenberg magnet. So now infinite temperature means the spins are completely disordered, completely random, and you now place an extra spin up in the center and you measure the spreading of this extra spin. Then this would follow the not a simple Gaussian, but this special Kpz scaling function, where the width now of this distribution would grow in time like 1 over z. Okay, so it would be a special scaling function with the universal kind of here argument where x divided by t over 1 over z, with z being the dynamical exponent, is this argument which gives us the universal distribution. Alternatively, what Thomas actually, Thomas Krosen actually showed in his group is a better way to measure this is not just to put a single spin here and measure how it propagates, but to look at this in a domain wall that we prepare in the spin profile. And the claim was that the propagation of this domain wall, how it spreads in time, will also be able to measure this dynamical exponent. Okay, so let's do that. So we have a conjecture. So let's test the conjecture, right? So we can do an experiment and test all of those things that come with this Kpz universality. So we do this in the Heisenberg chain. So we have to go to the point where delta equals 1 to the perfect Heisenberg chain. And we have to go to the point where we have zero magnetization and a purely 1D system, and check whether the predictions of Kpz universality actually are fulfilled here. One of the predictions is that we have super diffusion, that space and time are connected to each other not by 1/2, as we would have in a normal diffusion process, but by this new dynamical variable z, which is 3/2. So space and time should be connected to each other by 2/3. That's one prediction, but there are other predictions we have to look at. Then we can check, how sensitive is the system reacting to when we break these fundamental assumptions. So we break integrability by going from 1D to 2D, or we break magnetization by breaking the SU2 symmetry. So trying to understand what is really crucial to see Kpz superdiffusion. Okay, so we do the experiment. Now comes the box, finally, Thierry. The box, completely homogeneous system, about 1,000 atoms, chains of length of 50 atoms. So that's nice, 50 atoms, and we have about 14 to 20 chains here. And we think of these as individual 1D chains going in this direction, and we can have transverse coupling, which I can also tune in the system. And we can prepare the left half of the system in a spin up state, the right half of the system in a spin down state, and then evolve the system as a function of time and see how, for example, the spin ups propagate into the spin down region and the spin downs propagate into the spin up region. During all this process, the density remains completely fixed at 1. There are no density fluctuations. So it's pure spin dynamics that we're looking at. And here's, for example, a single snapshot where we see this 50 site long chain, where we've measured, for example, the position of the spin up atoms on that chain. Okay. All right, we can do that with a so-called clean domain wall, but we can also do this with a domain wall of reduced contrast, which is actually important in the problem. I don't want to go into the details of that right now, but you can see we can also make a domain wall which has less contrast. So on the left half of the system, the spins are a little bit more spin up. On the right half of the system, the spins are a little bit more spin down. Okay, so the contrast of the domain wall is reduced. Okay, so first thing we measure is polarization transfer. So we see the spins that are moved from left to right. So I can just measure how many spins have been transferred as a function of time. And that should scale, this number, the polarization transfer, should scale like t to the 1 over z, with z being the dynamical exponent 3/2. Here's the data. Here are these spin profiles at different evolution times. And if we measure the polarization transfer and we fit with an exponent to it, we get an exponent of 1.54 with an error of 7. So actually quite good agreement with this 3/2. We also see that if we scale these spin profiles with this Kpz scaling function, or the integrated Kpz scaling function, they all collapse. Okay, so here's this scaling parameter, the spin profiles at different evolution times, they all collapse. And we can also compare how this polarization transfer would look like for a ballistic case, where z is 1, where we have ballistic transport. This would be the blue curve here, or where we have basically just diffusive transport, where we'd have 1/2. This would be the red curve. So clearly, very nicely distinguishable that we have super diffusion in the system. Let's break integrability. Let's introduce the coupling between the chains. When we break integrability in the system, we actually can do the same measurement again. That's actually the same for us to do. And we indeed see that we go from this 1.5 to 2 to diffusion. So for 2D, this is not present. We go back to diffusion again. We can also break the SU2 symmetry by magnetizing the system. So now we go from an unmagnetized system where we have equal amounts of spin ups and spin downs to a magnetized system. And there you can also immediately see same parameters, but completely different evolution. You can now see kind of this large, very fast particles following this kind of ballistic trajectory here. We can again measure the transport coefficient, and we can measure that. Turns out to be 1 in the case of this magnetized system. So let me recap. 1D unmagnetized dynamical exponent of 3/2. 1D magnetized ballistic transport, Z = 1. 2D unmagnetized system, diffusive transport with a dynamical exponent of 2. So we have to be at this special point to see that. Now let me give you an even stronger argument. So this transport superdiffusion itself is not a priori proof of Kpz. You need to dig a little bit deeper. And remember what I told you about the Kpz equation. It was all about the fluctuations, about Kpz universality, that the fluctuations of the height field scaled like t to the 1/3, and that the underlying distribution function was this non-symmetric distribution function that we had in the system. Okay. It turns out that these height field fluctuations directly map onto our polarization transfer fluctuations. What the height field fluctuations are in the Kpz are for us the polarization transfer fluctuations. So remember, we measure in each shot, we measure a number of spins that have been moved from left to right. Okay. So from that, I can of course measure a distribution function. If I plot how many spins have been transferred after some evolution time. And this is what we show here. And we basically can calculate, this is the distribution function we measure, polarization transfer at some evolution time. And from this distribution function, we can calculate the skewness. You know, how skewed is this distribution? Remember, for a Gaussian process, this should be symmetric. For a Kpz class, this should be skewed. This should basically be a skewness. And the skewness, the distribution function, this Tracy-Widom distribution, which type of Tracy-Widom depends a little bit on the initial conditions. But you can see actually, indeed, we see that as a function of evolution time, we see the skewed distribution, and the skewness does not seem to decrease with evolution time. In 2D, if you just have linear transport, there's a completely different thing that happens here, that basically the skewness just goes to 0 because you're more and more approaching these Gaussian fluctuations, okay, in the diffusion process. We can also check the 1/3. What's the scale of the fluctuations? So what's the standard deviation of this distribution? Okay, what are the scale of the fluctuations? How do they scale as a function of time? And here you can see the green curve again being the 1D situation, brown curve, the 2D situation. For the green curve, we get a standard deviation. It evolves as a function of time with an exponent of 0.31. Actually, very good agreement what we expect for the 1/3 in the Kpz universality class. Okay, that's nice, because I think we can summarize our findings now. You know, I think we have several experimental findings that indeed we have Kpz universality in this infinite temperature Heisenberg spin transport. We have super diffusive transport. Problem is that alone is not a strict proof of Kpz universality. You can get that from different linear transport models as well. We see polarization fluctuations that scale indeed with an exponent beta 1/3. We see a skewness of the polarization, which seems to be compatible with the Tracy-Widom GOE or GOE distributions. And we see that this is very sensitive on that you have SU2 symmetry, and you would have an integrable system underlying this. And a deeper understanding, I think, of this phenomena, why we have Kpz is still outstanding. There are some explanations. So I think this is really something also where you can contribute in trying to understand this. Also, the mapping to the Kpz equation of the spin transport is still kind of an open question. But I think we've given new evidence that indeed Kpz universality is present in this system.
So Immanuel?
Yeah.
There's this mapping for 1D. Do we expect there to be a similar mapping for the 2D, 3D, 4D?
Well, we don't really completely understand the mapping in 1D even yet, I have to confess. So what equation? So I should say Kpz universality is a little bit different than the Kpz equation. Kpz universality is these universal exponents that I talked about. And it might sound crazy, but for a long time, it wasn't even known whether the Kpz equation, the solutions of the Kpz equation lie in the Kpz universality class. That was only actually recently shown that that's indeed is the case. So the mapping is not completely clear. I think it's not completely worked out. We're trying to work it out together with our collaborators. The results have invoked a lot of interest, so we're working on this. And yeah, we don't expect this in 2D to work. Okay, so in 2D there is no mapping. There's just linear transport. There's just diffusion again. So it's really a 1D phenomenon.
Right.
Okay, yeah, let me just wrap up and just say where next. You know, you've heard these beautiful experiments on ion traps, on tweezer arrays, on ultracold atoms, and I think they all have their pros and cons. Clearly, the lattice systems, you know, are really nice. They allow us to make large systems, degenerate systems, but all of this is very much moving together. I think, as you also saw in the talk of Adam, all of these fields are moving very close together to each other. Let me just throw some pictures where we stand in system size. So right now, the largest system sizes we can do are about a few thousand particles, about 2,500 atoms in these box-shaped potentials. We're working with this cavities that you saw on this picture actually here, with making large-scale cavities to increase the system sizes even more. So maybe we can hope in the future we can go to several tens of thousands of atoms in such systems and use the same, you know, control techniques that I've introduced to you today. But this is just where we stand today already. And this is nice. These are much larger system sizes than we had before. We can have really good control over the potentials, homogeneous systems. So I think a lot of the stuff that Thierry always wanted us to do, maybe we can finally do now in these systems. And yeah, so a lot of goes, of course, into technical developments, developing these tools to project these potentials, box potentials, wires, arbitrary lattice potentials onto the atoms. And that's where a lot of our technical effort goes. And of course, I didn't expose you to this. This is our stuff that we have to do as experimentalists, but that's where we're really working on hard. Yeah, and I hope I was able to show you in these 3 lectures, you know, some aspects of the physics in these systems. We're mainly focusing on MBL, non-equilibrium dynamics, but of course there's much more. And that makes these systems really, I think, very, very exciting to probe. And let me just finally give credit to the people who have been doing the work with me on these experiments. So there's the Fermion team, where Jaya was responsible for the spin charge separation. Janis did the polaron experiments. Sarah and Dominic are the new PhD students in the experiment. And this was actually led for a long time by Christian Groß, who's moved to Tübingen now. And our rubidium team, where we had this nice collaboration with Norm's team, where the new results on Kpz Universality are mainly the work of David and Tony, who is now back in Barcelona actually again. All right, and yeah, we just finish off, and thank you for your attention. And yeah, if you want to come and work with us, please do. We cordially invite you. We always have openings for, you know, motivated people to join us in Munich. It's a nice environment, as you can see here. Not only science-wise, but also landscape-wise, and yeah, open to any questions you have in the remaining time. Thank you.
Thank you very much, Immanuel. I think now, having done 3 lectures, I think clapping is appropriate. So, all right. So, questions.
If you move away from the Heisenberg point, like delta equals 1, does that Kpz in 1D still survive?
No, the conjecture is no, does not convive. It only survives at the Heisenberg point. I mean, actually, we know that we have in the XXZ model, if the XX term dominates, we have ballistic transport, and if the ZZ term dominates, we have diffusive transport. So it's again a very special feature of the Heisenberg point. SU2 symmetry, so equal spin up and downs in the problem, and integrability. So all those things seem to play an important role here. And again, a really deep understanding why that's the case has to be worked out still, I think. And for me, it's amazing, the Heisenberg model, if you thought, do we still have open problems on the transport in the Heisenberg model, the oldest spin model we have, that this is only discovered just a few years ago. This is really remarkable to me.
There was this I guess in the group of Wolfgang Ketterle, right, they had some spin spiral in the Heisenberg model. They vary delta and C diffusion, subdiffusion, superdiffusion. Do you know if it's anything related to that?
Yeah, it's related. And we did the experiment actually in the Heisenberg case. We had an earlier experiment on that where we did that, pioneered that in our group. We did it at the Heisenberg point. The nice thing that Wolfgang was able to do was to tune through the XXZ parameter space. But in the spin spiral measurements, you do not see this. You do not see that super diffusion. You do not see Kpz universality. Indeed, we saw in our experiments, and also if you look at Wolfgang's data, the dynamical exponent is really closer to 2 than to 1.5. And we did the experiment before Wolfgang. We got a dynamical exponent of 2. We redid them with a spin spiral. In this experiment, again, exactly this setup that I showed you, you get a dynamical exponent of 2. And it's not really also quite well understood why one measures something different there. Maybe it has to do because you're measuring a spin spiral. You're not in the linear response regime there because you're measuring really the large spin spiral contrast. And so maybe if you would be in linear response with a smaller spin spiral contrast, you could measure it. But honestly, I have to say it's not exactly understood why it's different, but it is different. And we looked at it again in the system. And again, measuring just the dynamical exponent, you do not prove Kpz universality. That's also an important point. So superdiffusion alone is not a proof of Kpz universality. Okay, any more questions? You're exhausted. I will post the slides tonight, so you'll have them, everything I noted on them, I'll post them.
I have a question, Immanuel. And this is very related to my personal interest. If I had generalized your system to SUN instead of SU2, do you have any intuition whether it would still be Kpz or something else?
I don't know. I don't know. A good question. I don't know.
Where's the best thing that I can learn to get some intuition for this mapping? Is it your paper or?
Well, I have some references in the slides, which I think is good starting points for reading on this. So mostly this stuff here, this page here. So
Perfect.
I think you can read more about it. But yeah, it's a good question, Caden, actually. Yeah, should work this out. Absolutely. Actually, we know there are other models. It also for Fermi-Hubbard also lies in the Kpz universality class. So there was a paper from who was it in Oxford? I'm forgetting the name now.
Probably.
Sorry, no.
Probably no, not Fabian. Okay.
It was it was not Esler. Anyway, so for Fermi-Hubbard, we also know, which is interesting because here we have an underlying Bose-Hubbard model, which actually, and for Bose-Hubbard, we know because Fermi-Hubbard is integrable in 1D, Bose-Hubbard is not integrable. Yep. So actually, it's also interesting, would be interesting to check if we go from the Heisenberg point of very strong interactions to weaker interactions where we are more like Bose-Hubbard model, then we should not see Kpz universality. Whereas if you start with a high fermionic system, which also tunes to the Heisenberg point at strong interactions, you have Kpz universality, but when you tune away to weaker interactions, you should actually retain Kpz universality there. That's the prediction.
Yep.
Yeah, that's interesting. Yeah, I forgot to mention that. Good point.
Can I ask a question? Can you also do more conventional spin transport by imbalancing the ends of your very long chains now, fantastically long chains? 50 is very nice.
Yeah, sure. We can do crazy initial states. We can even do a Néel state in one half, a ferromagnetic state in the other half, and there's a lot of stuff we can play with. So you have to tell me what we should look at, and yeah, there's a lot of
we should discuss.
Stuff.
Yes.
Yeah. This gives us a lot of potential. And as you can see, we can control these domain walls really down to the level of a single site. They're really super sharp domain walls.
And you can control the J-perp also, which means you can study confinement, deconfinement. Okay, fantastic.
Yes. Okay. Well, if you have any more questions, of course, feel always free to drop me a note. If there's any questions or things that come up afterwards.
All right. Thanks very much, Immanuel, for the wonderful series of lectures. And given that it is getting late there in Munich, have a great evening.
Yeah, it's getting, sun's going down. All right. Have a nice day, everybody. Bye-bye.
Bye.
Thanks, Emmanuel. See you.
Bye.
And then for the remainder of the lectures, I remind you that James Thompson will give his next lecture at 2 o'clock this afternoon.